Welcome everybody to this Dynaflow Research Group webinar. This webinar is part of the DRG Webinar Series 2015. In this webinar, I will discuss unbalanced loads in piping systems, where do they come from, and how can they be analyzed conveniently. It is important that unbalanced loads are considered since pressure surges in piping systems may result in high unbalanced loads and/or potentially unacceptable conditions. These unacceptable conditions may lead to various problems that may affect the integrity of the system, which ought to be a concern to the piping engineer. In this webinar, DRG provides a detailed overview of the cause and effect of surge waves. In addition, a short demo is presented where dynamic loads are easily determined in Bos fluids and used in a dynamic analysis in CESAR 2. My name is Daniel van Balen and I'm an engineer at Dynaflow Research Group. Before we begin, I will give a short introduction to Dynaflow Research Group. DRG is a leading engineering consulting firm focusing on three activities: consulting, which is the engineering section of the company; software development and sales. We develop several software packages ourselves, for example Bos Fluids and Bos Pulse for flow and pulsation analysis; and training, which includes conferences and lectures, but also this webinar series. On this slide you can see our engineering services. As you can see, we focus on a multitude of services related mainly to the oil and gas industry. Flow assurance is a service that returns in a significant part of our projects. This webinar discusses a phenomenon that often plays a leading role in these flow assurance projects. It is important to note that this webinar is based on the DRG Bos Fluids training course, which is a 2-day course focusing on the various facets of flow assurance and of course Bos Fluids. So for a more in-depth discussion on these topics, I would like to refer you to our website. So surges are variations in pressure that are generated by a change in the operational status in the system. This could be foreseen operational changes like pump startup or valve closure, or unforeseen operational changes like pump trip, for example. Surges can lead to unanticipated or anticipated effects such as extremely high or low pressures and unbalanced loads. So unbalanced loads are the result of a pressure surge traveling through the system. But how does this happen? In steady state, there is a force equilibrium between one elbow pair as shown in the left figure. The difference between the loads on the opposing elbows is caused by friction forces acting on the fluid and the pipe. In this case, the valve friction is in equilibrium with the loads on the elbows. In the case of a transient upset scenario, however, a pressure wave travels through the system, resulting in a large differential pressure between opposing elbows. Since fluid velocity is generally low in the case of a surge wave, friction forces can be neglected. The net pressure difference between elbow pairs, delta P, multiplied with the internal area of the pipe results in the unbalanced loads acting on the pipe section. Other than unbalanced loads, pressure surges may also lead to overpressures, which may lead to permanent deformation or rupture of the pipeline element, or underpressure, which may cause collapse of the pipeline or leakage at joints and seals under subatmospheric conditions. Reverse flow can cause damage to pump seals and brush gear on motors, draining of storage tanks and reservoirs. Pipeline movement and vibration could directly overstress supports, causing support failure that subsequently leads to failure of the pipe. As mentioned earlier, flow velocity in the case of surge is generally low. In case of slurry lines, this could cause settlement of entrained solids and line blockage. Surges are basically pressure waves running through the system. Pressure at a system node varies over time due to a pressure wave passing by and being reflected at the end of the system. As illustrated in this figure, surge pressures can rise and drop to significant levels above and below steady-state pressure. In summary, pressure pulsations propagate through the pipelines at the speed of sound in the fluid or gas running through the pipe. Propagating pressure pulsations cause time-dependent unbalanced forces between the consecutive elbow pairs. The unbalanced forces generate a dynamic response of the piping system that may affect the integrity of the system, which should be of concern to the piping engineer. For convenient analysis of the unbalanced loads and accurate prediction of the fitness for purpose of the system, you need a tool to predict the magnitude and time history of the unbalanced loads. Bos Fluids is such a tool. In the remainder of this webinar, I will show how the unbalanced loads can easily be determined in both fluids and exported to CESAR2 for dynamic analysis. In addition, I will show how various factors impact the surge wave and unbalanced loads in the system. In this demo on fluid transients, we start with a simple piping model with several straight sections and a valve imported from CESAR2. The line runs from an upstream basin with a fixed head of 6 bar to a downstream vessel with a fixed head of 5 bar. When we run the model without any upset scenarios, we obtain the steady-state solution. When we plot the pressure over the entire length of the system, the gradual pressure drop due to wall friction is observed. We can also see that there is some elevation difference in the model. See, the lower section there results in a higher pressure due to the pressure head of the fluid. You can also see the pressure drop over the valve here. But we are not interested in a steady state, we are interested in an upset scenario. We can introduce an upset scenario through the Scenarios menu. In this scenario, we will close the valve and see how this affects the fluid flow in the system. Let's close it in 10 seconds after 1 second of simulation time. Of course, you could add a more detailed closure curve, but for now we keep this simple linear closure curve. We now run the model. If we plot the pressure close to the disturbance, the closing valve in this case, we see the pressure starting to oscillate. When the valve closes at 11 seconds, the moving fluid has no info yet that it cannot continue to flow, and thus continues to flow towards the closed valve, resulting in the first pressure peak at 11 seconds. This increased pressure downstream causes the flow to decelerate and reverse direction upstream of the valve. Because the flow now flows towards an open end, the fluid will exit the pipe, causing a reduction in pressure. The reduced downstream pressure then causes the flow to return into the pipeline and fill the line again, resulting in the next pressure peak, and so on. As we plot the pressure profile over the length of the pipe, it can be seen that the pressure wave travels through the system. Since the pressure peaks moves through the system as a wave, a differential pressure between elbow pairs results. It can be seen that a longer section of pipe will be able to facilitate a larger pressure difference, resulting in a larger unbalanced load. This can also be seen when we plot the force instead of the pressure over the length of the system. So now we can clearly see that the first high force corresponds to the first section. The second section, the longer section, results in a higher unbalanced load. Then we have some small sections in between and another longer section resulting in a larger force. Now what will happen if we add another scenario where we close the valve faster? Now we will close the valve in 5 seconds and see how this impacts the fluid flow in the system. As we run the model, we see that it skips the first 2 scenarios since these scenarios didn't change. When we compare the first 2 upset scenarios, we see that the faster closing valve results in a higher pressure difference caused by the more abruptly closing valve. Also, the initial pressure rise is sharper due to a faster closing valve. We can also see that because the valve closed in 5 seconds, it is completely closed 5 seconds earlier than the other scenario, resulting in an earlier start of the pressure oscillation. Also note that the period of the oscillations didn't change. The period of the oscillations is related to the length of the system. Since we are dealing with an open-closed system, the return period for the pressure wave is calculated by 4 times the length of the system divided by the speed of sound. We can easily illustrate the effect of the length of the system on the period of the pressure oscillations. We make another scenario and add a special pipe element at the beginning. We will add a pipeline element where we can specify the length of the system. The length of the system is 145 meters. If we add another 145 meters, we have doubled the length of the system. With a longer system, the pressure wave has to travel twice as far. so the period will have roughly doubled. If we plot the second upset scenario for both lengths, we see that the period has indeed doubled. Another difference is that the amplitude of the longer system is higher. This is because the longer system can accommodate more water, which takes longer to come to a stop when the valve is closed. Other factors that influence the frequency of the oscillations are the fluid type, temperature, and to a lesser extent also pipe material because of their impact on the sound speed. The pressure rise for an instantly closing valve can also be determined analytically using the Joukowsky equation. To show that the Joukowsky equation calculates the same pressure rise as Bose fluids, we add another scenario where we close the valve instantly, because the Joukowsky equation calculates the pressure rise for an instantly closing valve. So when we add another scenario where the valve closes much faster, we can compare the Joukowsky pressure to the pressure calculated in Bose fluids. Joukowsky states that the pressure rise is the product of the change in velocity, the sound speed, and the density. We check the steady state velocity as 4.3 meters per second. The sound speed in this system is 1300 meters per second, and the density of water is 1000 kilograms per cubic meter. This yields a Joukowsky pressure rise of 55.9 bars. Adding this to the steady state pressure of approximately 5 bar and comparing this to the computed pressure rise in Bose fluids, we see that the pressure indeed approaches the Joukowsky pressure of 60 bar. So it can be seen that Joukowsky offers a convenient way to get an initial estimate of the pressure rise due to a safety valve or another fast closing valve. Now we have determined the unbalanced loads due to an upset scenario. They can be easily exported for further use in the stress analysis. In order to be able to export the unbalanced loads, we have to fill out the force pairs first, which are basically the nodes of the elbow pairs where we want to export the forces. We will export the forces of the three longer sections because the highest loads were observed at these locations. Before we export the unbalanced loads, I will first check the magnitude of the loads for verification in Caesar later. The first unbalanced force is roughly 82 kilonewtons. The force in the second straight section is 111 kilonewtons. The force in the last straight section is 53 kilonewtons. Now all the force pairs have been added. They can simply be exported through the tools menu at the top. When exporting, you can choose which unbalanced loads to export for which load case. For this demo, we will choose the scenario where we increase the length of the system. You can also choose the file type. Here we will choose Caesar 2 for easy importing in Caesar later. In Caesar 2, we have the same model, but now we also have the restraints in the model. There are several guides and rest supports, and in every longer section there's also an actual stop. The first one, here's the second one, and the third one at the end here. Before we can do any dynamic analysis, we first have to run the static model. As you can see, in this model we only have the standard load cases. Now we can fill out the dynamic stress analysis. We will select time history because the forces exported by Bose fluids also contain the time vector. The forces exported from Bose fluids can be directly used in the dynamic solver in Caesar 2. Here we have to fill out the files that contain the forces exported by Bose fluids. For our model, the coordinate system in Caesar 2 and Bose fluids are identical, so the direction filled in here can correspond to Bose fluids or Caesar. However, when the coordinate system in Caesar 2 is different than in Bose fluids, you have to be careful to make sure that the forces act in the correct direction. The load case that we enter here is for the combined static plus dynamic loads. Since I will only show that the unbalanced loads calculated in both fluids indeed act on the piping supports, this input doesn't matter. Of course, we also have to include the dynamic loads. For this demo, we will set the number of eigenvalues calculated to 1. We can leave the default input for the other variables. Now we can run the model and see if the unbalanced loads imported from both fluids indeed act on the axial stops in the system. The load on the axial stop in the first section is 81 kilonewtons. The load on the second axial stop equals 109 kilonewtons. The restraint load on the axial stop in the last section is 52 kilonewtons. As expected, these loads correspond to the unbalanced loads exported from both fluids and act in the correct direction. I will now conclude this webinar by thanking you for your participation. For a more in-depth discussion on flow assurance, please refer to our Bus Fluids training course. Furthermore, it may be interesting for you to note that DRG will host the third conference on flow problems in the oil and gas industry on the 23rd of September in Rotterdam. For more information and subscription, please visit our website. I will now answer some questions. You can still ask any questions in the chat window in your GoToWebinar control panel.